backbone curve. It is given m versus theta. This is denoted as A in ASC 41. Okay. This is denoted as B and this is denoted as C. Okay. So these values of A, B and C depend on rho minus rho dash over rho balance. Okay. And this also depends on V over VD FC dash. We are using FC dash. Okay. So this is representing whether our section is under reinforced or over reinforced, or how much under reinforced. Okay. So rho is volumetric ratio or area ratio of reinforcement. If this beam is subjected to sagging, that means tension is at the bottom, then this is rho dash, this is rho, and if tension is at the bottom, then this will be rho, the tension reinforcement, this is rho dash, the compressive reinforcement, okay, and rho balance is corresponding to balance failure, okay, which you have calculated in IS 456. So you take this as 0.0035, this you take Fy or Fy over Es plus 0.2. In our case, when we are using expected, you can take it as expected. So this will give you the balance failure reinforcement. This condition. Okay. So this term you will get from here. Second term is this V is applied base shear. Sorry, applied shear force, not base shear. Applied shear force. And BD is square root FC dash. This is representing shear capacity. It's not equal to shear capacity because a factor will come. This is proportional to shear capacity. The square root FC dash is proportional to shear strength of concrete, and BD is the area. B is the applied shear. Okay, so applied shear will depend on how that member, how that section is used. For example, it is a beam section, then how much will be the applied shear? Capacity shear. So you can calculate the capacity shear. If it's cantilever, then how will be the shear? Moment divided by length. If it is column, then how will be the shear force? It will be that. When the column itself is yielding. So similar to beam, you can calculate the shear in the column. Okay. So this shear force is when the yielding is occurring in the member, not the shear force which you are getting from analysis under dead load and live load. Okay. The shear which will be occurring at the time of yielding of that. Okay. So when yielding of the member will occur, depending on its length, you can calculate the relationship between moment and shear, and that shear force you can use. Okay. And then there is a third factor also, which is C or NC. So that perhaps you understand. Conforming and non-conforming. Conforming if the detailing is done as per detailing code. In our case, IS 1392. Okay. And non-conforming if the detailing is not as per IS 1392. So naturally, when you have done detailing, values of A and B will be more. When you have not done detailing as per ductile detailing code, then value of A and B are going to be less. Okay. In case of column, right. So ASC 41. ASC 41 deals with existing buildings. Okay, that's why it deals with C and NC both. But in a new structure, when you are designing a new building, there will not be any NC. You will always have conformity. Similarly, the capacity shear design may or may not be done. So in a member, if capacity shear design is performed, okay, it is designed for capacity shear, means its failure in shear is protected. That means it will fail if failure in shear is protected. What does that mean? That before failing in shear, it will fail in flexion. So there will be flexion issue. Means case 1. But in an existing structure, this may not be always the case, depending on how much shear reinforcement is provided. So you will calculate the shear capacity and flexion capacity. If flexion capacity or let us say shear capacity is much larger than the flexion capacity, then this case will occur. Second situation may be there where the shear capacity is much smaller than the flexion capacity. In that case, failure will occur in shear. Okay. There is a third case also where flexion and shear capacity are comparable. In that case, what will happen? The failure or the yielding will start with flexion. Once flexion yielding occurs, the concrete will crack in tension, and then its area, which is transferring shear, that will reduce, and then the failure may be governed by shear. This is called flexure shear failure. So combined failure of flexure due to flexure and then by shear. You can see that the ductility in the three cases will be different. In which case we are going to get the maximum ductility? Flexure. When the failure is occurring in flexure, we will get the maximum ductility. And when the shear failure is governing, we will be brittle, we will have very little ductility. And in case of flexure shear failure, we will have some variability. So that's why those three conditions are there. You can check that the value of A, B, C are changing depending on whether it is flexure failure or shear failure or flexure shear failure. In case of a new building, if you are designing, you will not allow shear failure or flexure shear failure. It is desirable that shear capacity should be sufficiently larger than the flexion capacity so that the failure occurs in flexion. And the ductility you obtain, values of A, B you obtain are maximum. Okay. Any other doubt?
Sir, once discuss yield surface.
Sorry?
Yield surface.
Yield surface. Okay. So you are familiar with PM interaction curve. Okay. So in case of RCC member, we get PM interaction curve like this. Now at any value, what is it is giving that at any value of P here, we can read M from this curve. Okay. Now question is, when we are saying this axial force P actually, so at this axial force we can plot an M phi or M theta curve. And M phi or M theta curve will be something like this. So actually at any given axial force, this moment is varying. There is not one value of moment. There are multiple moments. So which moment is this? That's the question. So we can convert this into equivalent bilinear curve. Okay, then we can get My or we can get Mu. So two very common definitions of this moment which come to our mind are that this can be either My or it can be Mu. A third definition is there in case of ST16, that it may be limit state moment. What is limit state moment? It is Mu only. This is Mu, but it is ultimate moment, but it is calculated at a strain of 0.0035 or 0.004. Okay, and we use 0.67 FCK and Fy, and why 0.67? Because of the correction factors. So FCK is characteristic strength of Q. So to convert that into structural strength, we use this Fy, and then we use the partial factors of safety. Okay, that gives you Mu. Okay, if I have to calculate the actual Mu, how I will calculate? This will consist of the confined concrete strain. So epsilon CCU I will use in place of 0.67 FCK. I will use 0.67 FCE, expected strength, and that too confined. So let me call it FCCE. The confined concrete strength. I will use expected yield strength, and gamma will be equal to 1. Then it will give me Mu, the actual expected ultimate strength. Okay, I can calculate My also. How I am going to calculate My? Two methods we can use. Either we can calculate as My dash over 0.75, or I can calculate this as M 0.004. Both are approximate estimates of My. Approximate. My we are not calculating exactly. If I have to calculate My exactly, what I have to do? I have to plot the full curve. So I should get all these points. Then I should bilinearize this. Then I will get the actual value of My. Okay. So it is too much of computational work. You can do it using computer, but manually it is difficult. Okay. Already when I was asking you or enjoying, you were laughing. And perhaps reason was, what I can guess, that it is lengthy. Okay. So am I right? That is the reason why what you are not enjoying about that is that it is lengthy. You have to do too many calculations. So if I ask you to calculate actual My, you have to do it like this, which is quite lengthy. You can do with computer. But for manual calculation, you can use either this or this. Keep in mind, these are approximate. Slight difference, both are not going to give you the exactly same value. Slight difference is expected because we are approximating these. Okay. So when you plot P versus My, we call this as yield curve or yield interaction curve. And in case of nonlinear analysis, this is important to us. In case of design, this was important to us. In SP16 and limit state is given. Okay, so there that was important. But in nonlinear analysis, this is important. Why this is important? Go back to this curve. If we have to develop this curve, what I need? First I need this point B. And how I am going to get this point B? From my. So if I have to develop this for column, I need my. Okay, how to calculate my for a column? You will have to use, because it depends upon the axial force in the column. It is not constant. In case of B, my you can calculate directly. It is constant for a section. But in case of a column, it is no more constant. It varies with axial force. So whatever is the axial force in the column at the time of yielding, that axial force will decide that at what moment my column is going to yield. And you can see in case of earthquakes, axial force also goes on varying. Axial force does not remain constant. Okay. So every step when you are doing analysis, you have to check axial force, then you have to read the corresponding value of my, and then you have to decide whether the column is yielding or not, or at what moment this is yielding. So when we do a computer analysis, we need to provide this curve to the software. Either software has to generate this curve itself, or you have to provide. Then only the software can decide at what step, what value of my column is going to yield. Otherwise, you do not know. Okay, if you give one value, let us say you have given this value, and axial force changes, the value of my will also change. So that's why in case of nonlinear analysis, yield interaction curve becomes very important. Okay, and then what is yield surface? Columns are subjected to axial force and biaxial moments. So this is the axial force, and then it is subjected to moments in both the directions. You remember double arrow notation we have used for moment? So from right hand thumb rule, so these are subjected to moments in both the directions. So yielding does not depend on one moment, it depends on both the moments. Okay, so you have to plot PM interaction curve in terms of m by x and in terms of m by y. So first y represents yield, and x and y represent the directions, and this is, let us say, z. So x, y, okay, so z actually will be downward. So this is the positive direction of z. You remember right hand thumb rule? X to y, you will rotate. So this is x, this is y, this is z. Okay, let's say tension is positive, so compression will be this side. This is compression, this is tension. Tension we are taking positive at an axial force. So one interaction curve you will get with respect to x, another interaction curve you will get with respect to y, and in between, if you join them, so this will become yield surface. So actually you have to provide yield surface, not just yield curve, yield interaction curve. That is giving you when there is one moment acting about x or y. Actually there will be a combination of x and y. Then what the software will do, it will check first the axial force at any step, then it will see the mx and my which are acting on that point. Okay, then it will see that whether this point is inside the yield surface or on the yield surface. Okay, it can't be outside because yielding will occur, then moment cannot increase. Okay, so it will check that point. And if it is on the yield surface, it will, after that, it will invoke the plastic. So that means this point is reached. After that, this will come to reach. So this we call yield surface. In your case, the column is square. So column is square means that this PM interaction curve and this PM interaction curve will be same. How to connect them in between? Intermediate points. When you are doing numerically, you can calculate. You look at the section design. You have been taught in hands-on. You can generate this PM interaction curve at any angle. So there you will see it will generate at number of angles. Usually at every 15 degree, we generate similar curves. So we generate a curve here. We generate curves here and here, and then we develop this interaction surface. Okay. If you are doing manually, it will be too much to develop this curve every 15 degree. So in that case, if you look at IS 456, IS 456 gives you the equation of this curve in terms of mx and m1, m1 and m2, okay, or mux and my. So equation is given. Okay. So the equation of this curve is, at any angle, if you want to calculate, then it will be m by x to the power alpha plus m by y to the power alpha is equal to 1. And value of alpha changes along the height. So it is not circular. Okay. So just a minute. If this I am calculating, let us say, at an angle theta, this equation will not be 1. So at any angle theta, I can calculate m by the two components, m by x at theta, m by y at theta. Because if I am applying a moment, there will be two components. If the moment is at an angle, the resultant is at an angle, then you can have two components in x and y. So these are the components in x and y divided by the corresponding components m by x and m by y. What are m by x and m by y? When uniaxial moment is there. At that time, what is the yield capacity? Okay. To the power alpha, this should be equal to 1. And from here you can see that because of this, if there is a moment acting in m by y direction also, then the capacity in x direction is going to reduce. Then it will yield at lesser moment in x. Okay. If the moment is acting about x alone, then it can take this maximum capacity. But in between, both are going to reduce. It's okay.
Sir,
Yes.
how moment can occur at some inclination?
How moment can occur at
Some inclination at the
some inclination. Okay. Let's take an example of a building. Here are our columns. This building is subjected to earthquake force in x direction. But in reality, will it be subjected to only in x direction?
No.
It will be subjected to x direction as well as y direction. In reality, if you are considering the ground motions, if let us say this is the building, some instant earthquake acceleration will be in this direction, then in this direction, then in this direction, then in this. So I told you that not only the amplitude of acceleration is changing, ground acceleration is changing, its its direction is also changing. So it is sometimes it is in X, sometimes in Y, sometimes in Z. Okay. So actual analysis is quite complex if you want to do it for actual analysis. So what usually we do in time history analysis, we consider both the ground motions acting simultaneously. Alternatively, you can do separate analysis and X and Y also. And then you consider 100% in one direction and 30% in the other direction. The maximum moment you calculate. What does that mean? That these beams which are along X, these will be subjected to moment when earthquake in X direction is considered. These beams will be subjected to moment when the earthquake in Y direction is considered. But any column here, if I take a column, it will be subjected to moment when I am considering earthquake in X direction. So when I am considering earthquake in X direction, the moment about Y axis will be 100. And due to this Y direction, moment about X will be 30. So there is My as well as Mx acting. So this moment you can also show as vectors. So you can take out the vector resultant of this 100% that and 30% that. So this is going to be the direction of the resultant moment. So you can see that this resultant moment is at an angle theta. So either you can say that this is at an angle theta, or you can say that it is subjected to moment about both axes, biaxial moment. So this is what we call biaxial moment. Moment acting on both the axes. So that biaxial moment, resultant of that is given by an angle theta. Okay, and to treat this condition where the moment is acting in X as well as in Y, you have to use interaction surface, because one interaction curve can't decide that. You will need the interaction between the two moments, and capacity of that column in yielding will depend on how much moment is acting in X and how much moment is acting in Y direction, on the combination of the two. So this interaction surface is actually giving the yield point of our column when both the moments, biaxial moments, are acting on our column. Okay. In fact, while designing in the last semester, in our tutorial also, we have done design of a column subjected to biaxial moments. There we have used it. The same equation, we have used it there. So there also we have considered interaction. We have considered there a design PM interaction surface. So that was our design surface. That was neither yield nor ultimate. Okay, that was the design moment which we are using in our design, because that was calculated considering 0.0035 strain, 0.67 FCK, Fy and gamma. So that's how that surface which is given in SP16 we have. Yeah.
While calculating this PM interaction curve,
Right.
the question you have given P equal to 0.1 H into F1
Right.
Let's say only concrete.
Right.
There you have not considered steel. The example was taken by steel in column. Why?
Because at the beginning you do not know steel. So somehow I have to specify P. I can specify P as 1000 kilonewton, let us say. But then I should know what is this capacity. I have to calculate first now. Because maybe this 1000 kilonewton is outside. So that's why I have not given it 1000 kilonewton. I have given in terms of AG FC dash. AG FC dash is the axial force which concrete alone can take. Okay. So I have given, naturally the total capacity will be more than that.
Yes.
Because steel is also there. So steel I will come to know only after design. Okay, although in that question I have given, but in reality the steel you will come to know after design. So that's why it is traditional. There is tradition that P is represented as a factor times AG This is common to do that. Because AGFC dash, what it is giving? The axial force which can be registered by concrete alone. Naturally, the axial force which the section can register, including concrete and steel, will be more than this.
And what does that K will tell us?
K is the factor, that is 0.1 or so. For example, this point, okay, will be somewhere close to 0.4 AGFC dash. That has been seen from experience. Somewhere close to 0.4 AGFC dash we will get this point. Okay. So I have given 0.1 AGFC dash. 0.1 AGFC dash is in this range. And I have given 0.6 AGFC dash, that is in this range. So I have given you 2 points. One point is in tension control range, another one is in compression control.
Sir, this behavior interaction curve, we are finding capacity here for a particular section. Let's say one section, some reinforcement, 20%. Another section, 7 reinforcement, 30% reinforcement. Here, no, I know AST also size of section, also grade of concrete. Then I also know PU, means taken by steel and
You can calculate PU itself. You can calculate this capacity itself.
Then I know two things, steel also and concrete also. Then I can take actual capacity P equal to.
You can take.
Percentage of this.
You can take if you want. That's why I said it is fun. You can enjoy more. You can take that value of PU, not in terms of AGFC dash. You take in terms of actual capacity. You can do that as well. Okay. I did not want to do that calculation. That's why I have done it 0.1 AGFC dash. Okay. Because I did not want to go into that detail. That's why I have taken it. But you can take in terms of PU as well. You can calculate PU and then you can calculate in terms of that.
And sir, in case of concrete, we are assuming heating is occurring in concrete at 0.0015.
Yes. In case of unconfined concrete,
it is
we are assuming that it is a 0.015.
In concrete, we are testing concrete under compression. And under compression, how heating will take place? Like in tension, we can understand. To tension force, heating will take place. And in concrete also, it is taking place.
We discussed that, but I will repeat it again. So when we are testing a concrete cube or cylinder, generally we use cylinder to plot the stress strain diagram. Okay, you can plot the stress strain diagram. It will be something like this. Okay, this is 0.002 and this is called FC dash, the cylinder strain. Okay, now is there any yield point? But somewhere it must be yielding. So how to define yield point? I told you the method that wherever yield point is not clear from the stress strain curve, we do what? Equivalent bilinearization. So we will do equivalent bilinearization of this curve. Okay, so this is equivalent bilinearization. Then where is the yield strain? This is the yield strain. How much will be this? Less than 0.002. Roughly, it is taken as 0.001. So it is not actual yield point. Okay, because actual yield point is not defined from the stress strain. Okay, we are defining it by equivalent bilinearization. Okay, and that comes out to be close to 0.0015.
The meaning of heating is that, sir, increasing displacement without applying the force.
Yes. Conventionally, that is the meaning of heating.
Conventionally, that's the meaning.
Yes.
In stress can throughout this concrete where it is not showing like that anything.
Right.
Then how can we decide that heating is happening?
That's why we replaced it by this equivalent curve, equivalent bilinear curve. In this equivalent bilinear curve, what is happening after this point?
After this point, heating is happening.
That's why we are calling this as unit point.
Yes, but how can you ensure that that point is coming below before 0.002?
You can see if the area is to be equated, it can't be more than that. If the area of the two curves is to be equated, okay, I can't take it up to here.
At 0.002, cracking is forming.
At 0.002, cracking is forming. Now, cracking is forming much before 0.002. Micro cracks starts much before 0.002.
Okay, and then when the micro cracks is
At 0.002, the cracks develop. Okay, those are visible. And then the cracks expand, and thus when the concrete strength goes on reducing. So actually the cracks start much before 1
Sir, when we consider the yielding in concrete, strain we take at 0.0015, stress we will take from the original graph.
Right.
And in steel, yielding we take at Fy by Es, and there also the stress will be taken from the original graph.
Yes, theoretically it should be taken with the original curve, but in case of steel, that portion is very small. So even if you take it as Fy, it is not causing substantial error. So we have done an approximation there. Same curve is there in case of steel, it is like this. But as compared to the total curve, this portion is quite small. Here it is not so. Here, this curve is, this portion is small. So what we do is, when we develop equivalent bilinear curve, it comes out to be like this. And actually you should have considered this. But this difference is small. This difference is quite small, which you can ignore. So that's why we consider this itself as in case of steel. But in concrete we can't do that. Here the difference is more. Okay. Any other question coming to your mind?
Sir,
Yes.
can you draw ultimate moment capacity on say steel surface cover PMU?
Okay. So you want
PMU.
how PMU will look like. So this you can see from this curve. The relation difference between PMU and PMY will depend upon difference of this and this. So you can see in moment there is not much difference. At some axial force it will be slightly larger. MU will be slightly larger. At some axial force the MU will be slightly smaller than MY. So you can see at low axial force the moment curvature curve is something like this. So here you can see that My is slightly lower, Mu is slightly higher. Whereas here at high axial force, Mu will be actually slightly lower than M. So this curve, if I plot for Mu, it will be something like this. Here it will be slightly higher, and then it will be slightly lower. But it will be close. The difference is not much. You can see from it. So there is not much difference between MY and MU, but there is a lot of difference between phi y and phi. And hence theta y and theta u. So don't assume that MY and MU, sometimes we get this confusion because we are habitual to think in linear terms. Linear behavior. Behavior is not linear. Here MU may be still phi u is much larger than phi y. Okay? So linear behavior is only up to phi y. Beyond that, it is non-linear. Okay?
Sir,
Yes.
in the example of simply supported beam, how you have calculated delta P? Can you repeat?
In that question, I have given you the definition of M and theta in the question itself. So we have defined this as theta. And the moment which you are applying here, the same moment, equal and opposite, you are applying. Rather same, not even opposite. This is also anti-clockwise, sorry, this is also clockwise, that is also clockwise. Okay, and this is given as theta. I am asking you to plot the relationship between M and theta. So what will happen? Initially it is straight, then I have applied a small moment here, then I am increasing the moment. You can see that the point of counterflexion will remain same. Okay. Now suppose it has reached My. What will happen after that? Yielding has occurred. Then what is going to happen in this case? It is not like the cantilever. In cantilever, what was happening? This is the deformed shape. It increases, okay, and when the yielding occurs, this cord rotates and the deformed shape gets frozen. So deformed shape is frozen after that. It is rotating as a whole. What will happen here? If the plastic hinge is formed here and here, then what is going to happen? When you will increase the moment is not going to increase because it has yielded, but the rotation can increase. Okay, and this deformed shape will remain here, only this joint will go on rotating. Okay, so let us say this is your theta y, this is your theta p. So after that, there will be no more deformation because more moment cannot be applied. More moment cannot be applied. It is not going to deform. But rotation at the end can occur. It is like this. Or let me take fixed support here, then it is better. And I have a hinge here. Hinge, not plastic hinge. Hinge, the physical hinge. And I want to rotate it. What will happen if I rotate it like this? So the perpendicular to this will rotate. What will happen to the beam? Will there be any deformation in the beam? Beam will not deform. Okay. Same thing is happening here. Till the plastic hinge has formed, the deformed shape will go on changing. Okay. After the plastic hinge forms here, the rotation, that means the tangent at this point will rotate, but the beam will not deform anymore. Okay, so if you have to plot M versus theta curve, it will be like this only. And this you can calculate my theta y. How you can calculate my theta y? Because till it is deforming, you can consider this as consisting of two cantilevers. One cantilever on this side, another cantilever on this side. Okay, and okay, or you can also consider this as not like this. You can consider it as these two cantilevers. Because here is point of contraflexion, so these are joined here to it. Point of contraflexion, the moment is 0. Okay, and now I rotate this cantilever in this direction and this cantilever I rotate in this direction. So if this connection, the pin at the center was not there, these two cantilevers would have deformed like this. But because this pin is there, this pin will bring these two together. How can it bring these together? It has to apply a force here. It has to apply a force here. So due to this force, this is going to deform like this. This is going to deform like this, and both will meet at this pin. Okay. So can you calculate my in this case? How much moment will be required here at yield point? Let us say this is Qy. So if this angle is theta y, you know the relationship between my and theta y? You can calculate theta y in terms of my. Same as you have done in case of cantilever. So till yield point, these will be treated as two cantilevers like this, which are connected by a pin at the point of contraflexion at the midspan, and after that the rotation is free. Theta will go on increasing. Okay, is that clear?
Sir,
Yes.
at the end we can't treat it as big support.
We can.
We can't, because if we consider
See, what is the difference between fixed support and pin support?
in fixed support, there is a reaction moment which will make elastic rotation at that end equal to 0.
In case of pin support, the rotation is free.
Ah,
It can rotate the way it wants.
yes.
In case of fixed support,
It will not rotate at that point.
no. It will rotate equal to the rotation of support. Not that rotation is 0. It has to rotate as the support wants. So, for example, in case of a frame, we have considered two cases. In one case, we have considered these fixed. Another case, we have considered these as fixed or rigid. So what is happening? If the column is rotating like this, the beam also has to rotate like this. Okay. So similarly, fixed support of a cantilever, it doesn't mean that it will remain like this. If due to any reason the support rotates, then the member also has to rotate like this. So whatever is this angle, same angle has to be. So that is fixed support. Here what we are doing, we want to apply a rotation here or moment here. How can I apply moment at a free support? Suppose I want to apply a moment at free support. How can I apply? You want to rotate a beam. Suppose there is a bridge. Both hands are pinned. You want to rotate the beam at this hand. How you will rotate?
We have to go there and apply the moment.
How? How to apply a moment? Load you can apply, you can simply hang a weight or you can keep a weight. How you are going to apply moment? At any point, if you have to apply moment, how you will apply moment?
By giving a lever.
You have to create a lever also. Okay? So for applying moment here, you have to first bend a member like this, and then this member you have to push. Then only the moment will be applied. So you can see that this is same as this. So this condition is similar to this condition, and that's why I have converted this into equivalent. So in a free or free to rotate or simply supported, and if I have to apply a moment, there is no other way other than fixing it or connecting it with a lever and then applying the moment through the lever.
So in this case, after theta y, the further deformation of member should not be.
Right.
The joint will rotate.
Right.
Till when?
Till at this hinge you reach theta u. When this hinge, because rotation in this hinge will still continue. Okay. So whatever is the rotational capacity or plastic rotational capacity of this hinge, that much rotation will take place. If you rotate beyond that, it will fail.
Support will fail or member?
Member will fail because hinge is not in the support. Hinge is in the member. Very close to the support. But it is in the member. So it is the member which is going to fail, not the support.
Sir,
Because support is supported here. This is your member, and you have welded this and you are applying load. Hinge is forming here. So when this will fail, support is not going to fail. Support will remain in its place. The member will fail.
How will support rotate after theta y then?
Actually, we are not rotating support. We are rotating this end of the member which is at the support. Okay, and our plastic hinge is slightly inside.
sir,
Yes.
if I am considering UV and applying load on this, it should go like this.
Right.
Now if I am rotate this support, then this member will also rotate.
Right.
Like this.
Right.
Load will also rotate.
Right.
And then deflected shape will be like this.
Right.
Then this deflected shape is not similar to this deflected shape.
Okay. So one thing we have to note down here, that whatever we are doing here is involving small deflection. Whatever we are doing, still the deflections will be very small. For example, if you rotate this beam, apply a moment. Okay, is it going to come here? No. There will be very little rotation, hardly visible with eyes. Only when the cracks will occur, then you will be able to see. You can go and see some testing when it is going on in our pseudodynamic lab. Okay, you will see that the deflection of the beam and column is visible only at very end. Okay, initially you cannot, till yielding, till cracking occurs, you will not be able to even see the deflection. Okay, deflected shape will not be visible. So the rotations, diffractions are really small. Okay, so this angle here on the board I have shown like this. But if this has to happen here, this beam has to come here. Will it happen? It will fail much before that. So do not go by the exaggerated shape which I have plotted here. Actually this deflection is very small here. So you can see that this load will be still perpendicular to the beam. Okay. So all this we are doing small deflection theory, and our real structures have a small deflection even till failure. Okay. Otherwise, I have to consider this change in the angle. This load, okay, this will have two components. So I have to consider this component which is perpendicular and this component which is along the axis. The component which is perpendicular, that only will cause bending moment. This axial component will cause axial force, not the bending. Okay. But if this angle is small, then the perpendicular component will be same as the load and axial component will be zero. So that is the condition which we are considering in our analysis. Okay. So I'm happy you asked all these questions. These questions are very important. And yes.
Our in the question which is in prayer, our beam was like this.
Right.
So we are in a whole discussion. We are considering this as an arrangement equivalent to this fixed support.
Right.
And this is just a difference so that we can get that theta angle at this.
Right. To actually apply this moment, I have to hold the hand up. If I have to apply moment, what happens? Somehow I have to hold it, or I have to bend a lever to this. So this will be treated as if it is fixed, and I am rotating the fixed support itself. It is similar.
And then why you are taking that Q force at an inclined manner, this Q.
No, I am not taking inclined. I have taken it vertical. And I have taken it vertical. I am just showing that this vertical load will have two components. If I am considering that the rotation of the beam is large, suppose this beam was coming here, then what will happen? The vertical load will have two components, one perpendicular and one along. So this along will cause axial load, perpendicular will cause bending moment. But because this rotation is small, I can't plot that small rotation here and show you clearly. So that's why I have shown here large displacement. But actual in structure, it is not so large. This is small deflection. And when there is a small deflection, then vertical load is almost perpendicular to the rotated beam. Because rotation of the beam is very small. So even when the beam is rotated, the vertical load remains perpendicular. And we have ignored axial force, and we have considered the bending moment due to vertical load as if it is acting perpendicular to the member. Okay, so that is based on this assumption. If deflections are not really small, then we can't do this. Then we should take component of the vertical force perpendicular to the beam to cause it.
In case of contemplative check, somewhere in between above this here slope is like 0. So I am considering
No, not at all. It will be in case of a prompt cantilever. Okay, so if you rotate this, and here it is simply supported, let us say. So somewhere here, the maximum deflection will be created. This distance you have to calculate. This is not known. But if you can calculate this distance, then you can consider these two as the cantilevers. This as a separate cantilever and this as a separate. Then it is possible. But this distance needs to be calculated, which is not known. So that's why you can't convert these two, okay, initially into two cantilevers, because you do not know where this point of maximum deflection is going to occur. If you calculate that point of deflection, maximum deflection, then you can. Any other doubt? Yes. No, this is something different. This is interstory. So interstory drift is, it is neither yield nor ultimate. So when our building is reflecting, so this, let us say this is delta 1, this is, or let us start from the beginning. This is delta 1, this is delta 2, this is delta 3, this is delta 4. So this is delta 1 minus 0 divided by, let us say this height is h1, this is h2, this is h3, this is h4. So here you can calculate delta 4 minus delta 3 divided by h4. Here you can calculate delta 3 minus delta 2 divided by h3. Here you can calculate delta 2 minus delta 1 divided by dash 2, and delta 1 minus 0 divided by dash 1. All this should be less than this is the limit of interstory ratio. This is not a string. This has nothing to do with our 5004 string. This is something different.
Sir, in perfect object,
Yes.
in Boolean space relation as well as CC, you may have to everything integrate my that's why we can take to the third of like that.
See, if you have reached to the peak, then you can take 2/3. If you have not yet reached the peak, then it will be integer. Okay, so should we stop here? We will meet tomorrow.